12. The Earth Moves. In one of his last professional acts before his death in 1955, Albert Einstein wrote a short but glowing foreword to a book by a geologist named Charles Hapgood entitled Earth's Shifting Crust, a key to some basic problems of Earth science. Hapgood's book was a steady demolition of the idea that continents were in motion, in a tone that all but invited the reader to join him in a tolerant chuckle. Hapgood observes that a few gullible souls had noticed an apparent correspondence in shape between certain continents. It would appear, he went on, that South America might be fitted together with Africa, and so on. It is even claimed that rock formations on opposite sides of the Atlantic match. Mr. Hapgood briskly dismissed any such notions, noting that the geologists K. E. Custer and J. C. Mendes had done extensive fieldwork on both sides of the Atlantic and had established beyond question that no such similarities existed. Goodness knows what outcrops Messrs. Custers and Mendes had looked at, because in fact many of the rock formations on both sides of the Atlantic are the same, not just very similar, but the same. This was not an idea that flew with Mr. Hapgood or many other geologists of his day. The theory Hapgood alluded to was one first propounded in 1908 by an amateur American geologist named Frank Bursley Taylor. Taylor came from a wealthy family and had both the means and the freedom from academic constraints to pursue unconventional lines of enquiry. He was one of those struck by the similarity in shape between the facing coastlines of Africa and South America, and from this observation he developed the idea that the continents had once slid around. He suggested, presciently as it turned out, that the crunching together of continents could have thrust up the world's mountain chains. He failed, however, to produce much in the way of evidence, and the theory was considered too crackpot to merit serious attention. In Germany, however, Taylor's idea was picked up and effectively appropriated by a theorist named Alfred Wegener, a meteorologist at the University of Marburg. Wegener investigated the many plant and fossil anomalies that did not fit comfortably into the standard model of Earth history and realized that very little of it made sense if conventionally interpreted. Animal fossils repeatedly turned up on opposite sides of oceans that were clearly too wide to swim. How, he wondered, did marsupials travel from South America to Australia? How did identical snails turn up in Scandinavia and New England? And how, come to that, did one account for coal seams and other semi-tropical remnants in frigid spots like Spitsbergen, over 600 kilometers north of Norway, if they had not somehow migrated there from warmer climes? Wegener developed the theory that the world's continents had once existed as a single land mass he called Pangaea, where flora and fauna had been able to mingle before splitting apart and floating off to their present positions. He set the idea out in a book called Die Entstehung der Kontinente und Ozeane, or The Origin of Continents and Oceans, which was published in German in 1912, and despite the outbreak of the First World War in the meantime, in English 3 years later. Because of the war, Wegener's theory didn't attract much notice at first, But by 1920, when he produced the revised and expanded edition, it quickly became a subject of discussion. Everyone agreed that continents moved, but up and down, not sideways. The process of vertical movement, known as isostasy, was a foundation of geological belief for generations, though no one had any really good theories as to how or why it happened. One idea, which remained in textbooks well into my own school days, was the baked apple theory propounded by the Austrian Edward Suess just before the turn of the century. This suggested that as the molten earth had cooled, it had it had become wrinkled in the manner of a baked apple, creating ocean basins and mountain ranges. Never mind that James Hutton had shown long before that any such static arrangement would eventually result in a featureless spheroid as erosion leveled the bumps and filled in the divots. There was also the problem, demonstrated by Rutherford and Soddy early in the century, that earthly elements hold huge reserves of heat, much too much to allow for the sort of cooling and shrinking Suez suggested. And anyway, if Suez's theory were correct, then mountains should be evenly distributed across the face of the earth, which patently they were not, and of more or less the same ages. Yet by the early 1900s, it was already evident that some ranges, like the Urals and Appalachians, were hundreds of millions of years older than others, like the Alps and Rockies. Clearly, the time was ripe for a new theory. Unfortunately, Alfred Wegener was not the man geologists wished to provide it. For a start, his radical notions questioned the foundations of their discipline, seldom an effective way to generate warmth in an audience. Such a challenge would have been painful enough coming from a geologist, but Wegener had no background in geology. He was a meteorologist, for goodness sake, a weatherman, a German weatherman. These were not remediable deficiencies, and so geologists took every pain they could do to dismiss his evidence and belittle his suggestions. To get around the problems of fossil distributions, they posited ancient land bridges wherever they were needed. When an ancient horse named Hipparion was found to have lived in France and Florida at the same time, a land bridge was drawn across the Atlantic. When it was realized that ancient tapirs had existed simultaneously in South America and Southeast Asia, a land bridge was drawn there, too. Soon maps of prehistoric seas were almost solid with hypothesized land bridges from North America to Europe, from Brazil to Africa, from Southeast Asia to Australia, from Australia to Antarctica. These connective tendrils had not only conveniently appeared whenever it was necessary to move a living organism from one land mass to another, but then had obligingly vanished without leaving a trace of their former existence. None of this, of course, was supported by so much as a grain of evidence. Nothing so wrong could be. Yet it was geological orthodoxy for the next half century. Even land bridges couldn't explain some things. One species of trilobite that was well known in Europe was also found to have lived on Newfoundland, but only on one side. No one could persuasively explain how it had managed to cross 3,000 kilometers of hostile ocean, but then failed to find its way around the corner of an island 300 kilometers wide. Even more awkwardly, Anomalous was another species of trilobite found in Europe and the Pacific Northwest of America, but nowhere in between, which would have required not so much a land bridge as a flyover. Yet as late as 1964, when the Encyclopedia Britannica discussed the rival theories, it was Wegener's that was held to be full of numerous grave theoretical difficulties. To be sure, Wegener made mistakes. He asserted that Greenland is drifting west by about 1.6 kilometers a year, a clear nonsense. It's more like a centimeter. Above all, he could offer no convincing explanation for how the land masses moved about. To believe in his theory, you had to accept that massive continents somehow pushed through solid crust like a farm plow through soil, without leaving any furrow in their wake. Nothing then known could plausibly explain what motored these massive movements. It was Arthur Holmes, the English geologist who did so much to determine the age of the Earth, who came up with a suggestion. Holmes was the first scientist to understand that radioactive warming could produce convection currents within the Earth. In theory, these could be powerful enough to slide continents around on the surface. In his popular and influential textbook Principles of Physical Geology, first published in 1944, Holmes laid out a continental drift theory that was, in its fundamentals, the theory that prevails today. It was still a radical proposition for the time and widely criticized, particularly in the United States, where resistance to drift lasted longer than elsewhere. One reviewer there fretted, without any sense of irony, that Holmes presented his arguments so clearly and compellingly that students might actually come to believe them. Elsewhere, however, the new theory drew steady if cautious support. In 1950, a vote at the annual meeting of the British Association for the Advancement of Science showed that about half of those present now embraced the idea of continental drift. Hapgood soon after cited this figure as proof of how tragically misled British geologists had become. Curiously, Holmes himself sometimes wavered in his conviction. In 1953, he confessed, "I have never succeeded in freeing myself from a nagging prejudice against continental drift. In my geological bones, so to speak, I feel the hypothesis is a fantastic one." Continental drift was not entirely without support in the United States. Reginald Daly of Harvard spoke for it, but he, you may recall, was the man who suggested that the moon had been formed by a cosmic impact, and his ideas tended to be considered interesting, even worthy, but a touch too exuberant for serious consideration. And so, most American academics stuck to the belief that the continents had occupied their present positions forever and that their surface features could be attributed to something other than lateral motions. Interestingly, oil company geologists had known for years that if you wanted to find oil, you had to allow for precisely the sort of surface movements that were implied by plate tectonics. But oil geologists didn't write academic papers, they just found oil. There was one other major problem with Earth theories that no one had resolved, or even come close to resolving. That was the question of where all the sediments went. Every year, the Earth's rivers carried massive volumes of eroded material, 500 million tons of calcium, for instance, to the seas. If you multiplied the rate of deposition by the number of years it had been going on, you arrived at a disturbing figure. There should be about 20 kilometers of sediments on the ocean bottoms. Or put another way, the ocean bottoms should by now be well above the ocean tops. Scientists dealt with this paradox in the handliest possible way. They ignored it. But eventually, there came a point when they could ignore it no longer. In the Second World War, a Princeton University mineralogist named Harry Hess was put in charge of an attack transport ship, the USS Cape Johnson. Aboard this vessel was a fancy new depth sounder called a fathometer, which was designed to facilitate inshore maneuvers during beach landings, but has realized that it could equally well be used for scientific purposes and never switched it off, even when far out at sea, even in the heat of battle. What he found was entirely unexpected. If the ocean floors were ancient, as everyone assumed, they should be thickly blanketed with sediments, like the mud on the bottom of a river or lake. But Hess readings showed that the ocean floors offered anything but the gooey smoothness of ancient silts. It was scored everywhere with canyons, trenches, and crevasses, and dotted with volcanic seamounts that he called Guyot after an earlier Princeton geologist named Arnold Guyot. All this was a puzzle, but Hess had a war to take part in and put such thoughts to the back of his mind. After the war, Hess returned to Princeton and the preoccupations of teaching, but the mysteries of the seafloor continued to occupy a space in his thoughts. Meanwhile, throughout the 1950s, oceanographers were undertaking more and more sophisticated surveys of the ocean floors. In so doing, they found an even bigger surprise. The mightiest and most extensive mountain range on Earth was mostly underwater. It traced a continuous path along the world's seabeds, rather like the pattern on a tennis ball. If you began at Iceland and traveled south, you could follow it down the center of the Atlantic Ocean, around the bottom of Africa, and across the Indian and Southern Oceans, and into the Pacific just below Australia. There it angled across the Pacific coast of the United States to Alaska. Occasionally, its higher peaks poked above the water as an island on or archipelago, the Azores and Canaries in the Atlantic, Hawaii, and the Pacific, for instance. But mostly it was buried under thousands of fathoms of salty sea, unknown and unsuspected. When all its branches were added together, the network extended to 75,000 kilometers. A very little of this had been known for some time. People laying ocean floor cables in the 19th century had realized that there was some kind of mountainous intrusion in the mid-Atlantic from the way the cables ran, but the continuous nature and overall scale of the chain was a stunning surprise. Moreover, it contained physical anomalies that couldn't be explained. Down the middle of the mid-Atlantic ridge was a canyon, a rift, up to 20 kilometers wide for its entire 19,000-kilometer length. This seemed to suggest that the Earth was splitting apart at the seams, like a nut bursting out of its shell. It was an absurd and unnerving notion, but the evidence couldn't be denied. Then, in 1960, core samples showed that the ocean floor was quite young at the mid-Atlantic ridge, but grew progressively older as you moved away from it to east or west. Harry Hess considered the matter and realized that this could mean only one thing. New ocean crust was being formed on either side of the central rift, then being pushed away from it as more new crust came along behind. The Atlantic floor was effectively two large conveyor belts, one carrying crust towards North America, the other carrying crust towards Europe. The process became known as seafloor spreading. When the crust reached the end of its journey at the boundary with continents, it plunged back into the earth in a process known as subduction. That explained where all the sediment went. It was being returned to the bowels of the earth. It also explained why ocean floors everywhere were so comparatively youthful. None had ever been found to be older than about 175 million years, which was a puzzle because continental rocks were often billions of years old. Now Hess could see why. Ocean rocks lasted only as long as it took them to travel to shore. It was a beautiful theory that explained a great deal. Hess elaborated his arguments in an important paper, which was almost universally ignored. Sometimes the world just isn't ready for a good idea. Meanwhile, two researchers, working independently, were making some startling findings by drawing on a curious fact of Earth's history that had been discovered several decades earlier. In 1906, a French physicist named Bernard Brunhes had found that the planet's magnetic field reverses itself from time to time, and then the record of these reversals is permanently fixed in a certain rocks at the time of their birth, specifically tiny grains of iron ore within the rocks point to wherever the magnetic poles happen to be at the time of their formation, then stay pointing in that direction as the rocks cool and harden. In effect, they remember where the magnetic poles were at the time of their creation. For years, this was little more than a curiosity, but in the 1950s, Patrick Blackett of the University of London and S.K. Runcorn of the University of Newcastle studied the ancient magnetic patterns frozen in British rocks and were startled, to say the very least, to find them indicating that at some time in the distant past Britain had spun on its axis and traveled some distance to the north as if it had somehow come loose from its moorings. Moreover, they also discovered that if you placed a map of Europe's magnetic patterns alongside an American one from the same period, they fit together as neatly as two halves of a torn letter. It was uncanny. Their findings were ignored too. It finally fell to two men from Cambridge University, a geophysicist named Drummond Matthews and a graduate student of his named Fred Vine, to draw all the strands together. In 1963, using magnetic studies of the Atlantic Ocean floor, they demonstrated conclusively that the sea floors were spreading in precisely the manner Hess had suggested and that the continents were in motion too. An unlucky Canadian geologist named Lawrence Morley came up with the same conclusion at the same time, but couldn't find anyone to publish his paper. In what has become a famous snap, the editor of the Journal of Geophysical Research told him, "Such speculations make interesting talk at cocktail parties, but it is not the sort of thing that ought to be published under serious scientific aegis." One geologist later described it as probably the most significant paper in the earth sciences ever to be denied publication. At all events, mobile crust was an idea whose time had finally come. A symposium of many of the most important figures in the field was convened in London under the auspices of the Royal Society in 1964, and suddenly it seemed everyone was a convert. The Earth, the meeting agreed, was a mosaic of interconnected segments whose various stately jostlings accounted for much of the planet's surface behavior. The name continental drift was fairly swiftly discarded when it was realized that the whole crust was in motion and not just the continents, but it took a while to settle on a name for the individual segments. At first, people called them crustal blocks or sometimes paving stones. Not until late 1968, with the publication of an article by three American seismologists in the Journal of Geophysical Research, did the segment receive the name by which they have since been known, plates. The same article called the new science plate tectonics. Old ideas die hard, and not everyone rushed to embrace the exciting new theory. Well into the 1970s, one of the most popular and influential geological textbooks, The Earth, by the Venerable Harold Jeffreys, strenuously insisted that plate tectonics was a physical impossibility, just as it had in the first edition way back in 1924. It was equally dismissive of convection and sea floor spreading, and in Basin and Range, published in 1980, John McPhee noted that even then one American geologist in eight still didn't believe in plate tectonics. Today we know that the Earth's surface is made up of 8 to 12 big plates, depending on how you define big, and 20 or so smaller ones, and that they all move in different directions and at different speeds. Some plates are large and comparatively inactive, others small but energetic. They bear only an incidental relationship to the land masses that sit upon them. The North American plate, for instance, is much larger than the continent with which it is associated. It roughly traces the outline of the continent's western coast, which is why that area is so seismically active, because of the bump and crash of the plate boundary, but ignores the eastern seaboard altogether, and instead extends halfway across the Atlantic to the mid-ocean ridge. Iceland is split down the middle, which makes it tectonically half American and half European. New Zealand, meanwhile, is part of the immense Indian Ocean plate, even though it is nowhere near the Indian Ocean. And so it goes for most plates. The connection between modern land masses and those of the past were found to be infinitely more complex than anyone had imagined. Kazakhstan, it turns out, was once attached to Norway and New England. One corner of Staten Island, but only a corner, is European. So is part of Newfoundland. Pick up a pebble from a Massachusetts beach, and its nearest kin will now be in Africa. The Scottish Highlands and much of Scandinavia are substantially American. Some of the Shackleton Range of Antarctica, it is thought, may once have belonged to the Appalachians of the eastern U.S. rocks. In short, get around. The constant turmoil keeps the plates from fusing into a single immobile plate. Assuming things continue much as at present, the Atlantic Ocean will expand until eventually it is much bigger than the Pacific. Much of California will float off and become a kind of Madagascar of the Pacific. Africa will push northward into Europe, squeezing the Mediterranean out of existence and thrusting up a chain of mountains of Himalayan majesty running from Paris to Calcutta. Australia will colonize the islands to its north and connect by some Isthmian umbilicus up to Asia. These are future outcomes but not future events. The events are happening now. As we sit here, continents are adrift, like leaves on a pond. Thanks to global positioning systems, we can see that Europe and North America are parting at about the speed a fingernail grows, roughly 2 meters in a human lifetime. If you were prepared to wait long enough, you could ride from Los Angeles all the way up to San Francisco. It is only the brevity of lifetimes that keeps us from appreciating the changes. Look at the globe, and what you are seeing really is a snapshot of the continents as they have been for just 1/10 of 1% of the Earth's history. Earth is alone among the rocky planets in having tectonics, and why this should be is a bit of a mystery. It is not simply a matter of size or density. Venus is nearly a twin of Earth in these respects and yet has no tectonic activity. But it may be that we have just the right materials in just the right measures to keep the Earth bubbling away. It is thought, though it is really nothing more than a thought, that tectonics is an important part of the planet's organic well being. As the physicist and writer James Trefil has put it, it would be hard to believe that the continuous movement of tectonic plates has no effect on the development of life on Earth. He suggests that the challenges induced by tectonics changes in climate, for instance, were an important spur to the development of intelligence. Others believe the driftings of the continents may have produced at least some of the Earth's various extinction events. In November 2002, Tony Dixon of Cambridge University produced a report published in the journal Science, strongly suggesting that there may well be a relationship between the history of rocks and the history of life. What Dixon established was that the chemical composition of the world's oceans has altered abruptly and dramatically at times throughout the past half billion years, and that these changes often correlate with important events in biological history. The huge outbursts of tiny organisms that created the chalk cliffs of England's south coast, the sudden fashion for shells among marine organisms during the Cambrian period, and so on. No one can say what causes the ocean's chemistry to change so dramatically from time to time, but the opening and shutting of ocean ridges would be an obvious possible culprit. At all events, plate tectonics explained not only the surface dynamics of the Earth, how an ancient Hipparion got from France to Florida, for example, but also many of its internal actions, earthquakes, the formation of island chains, the carbon cycle, the locations of mountains, the coming of ice ages, the origins of life itself. There was hardly a matter that wasn't directly influenced by this remarkable new theory. Geologists, as McPhee has noted, found themselves in the giddying position where the whole earth suddenly made sense. But only up to a point. The distribution of continents in former times is much less neatly resolved than most people outside geophysics think. Although textbooks give confident-looking representations of ancient land masses with names like Laurasia, Gondwana, Rhodiana, and Pangaea, these are sometimes based on conclusions that don't altogether hold up. As George Gaylord Simpson observes in Fossils and the History of Life, species of plants and animals from the ancient world have a habit of appearing inconveniently where they shouldn't and failing to be where they ought. The outline of Gondwana a once mighty continent connecting Australia, Africa, Antarctica, and South America, was based in large part on the distributions of a genus of ancient tongue fern called Glossopteris, which was found in all the right places. However, much later, Glossopteris was also discovered in parts of the world that had no known connections to Gondwana. This troubling discrepancy was, and continues to be, mostly ignored. Similarly, a Triassic reptile called Lystrosaurus has been found from Antarctica all the way to Asia, supporting the idea of a former connection between those continents, but it has never turned up in South America or Australia, which are believed to have been part of the same continent at the same time. There are also many surface features that tectonics can't explain. Take Denver. It is, as everyone knows, a mile high, but that rise is comparatively recent. When the dinosaurs roamed the earth, Denver was part of an ocean bottom, many thousands of meters lower. Yet the rocks on which Denver sits are not fractured or deformed in the way they would be if Denver had been pushed up by colliding plates. And anyway, Denver was too far from the plate edges to be susceptible to their actions. It would be as if you pushed against the edge of a rock hoping to raise a rock at the opposite end. Mysteriously and over millions of years, it appears that Denver has been rising. Like baking bread, so too has much of southern Africa. A portion of it 1600 kilometers across has risen about 1.5 kilometers in 100 million years without any known associated tectonic activity. Australia, meanwhile, has been tilting and sinking over the past 100 million years as it has drifted north towards Asia. Its leading edge has sunk by nearly 200 meters. It appears that Indonesia is very slowly drowning and dragging Australia down with it. Nothing in the theories of tectonics can explain any of this. Alfred Wegener never lived to see his ideas vindicated. On an expedition to Greenland in 1930, he set out alone on his 50th birthday to check out a supply drop. He never returned. He was found a few days later, frozen to death on the ice. He was buried on the spot and lies there yet, but about a meter closer to North America than on the day he died. Einstein also failed to live long enough to see that he had backed the wrong horse. In fact, he died at Princeton, New Jersey in 1955 before Charles Hapgood's rubbishing of continental drift theories was even published. The other principal player in the emergence of tectonics theory, Harry Hess, was also at Princeton at the time and would spend the rest of his career there. One of his students was a bright young fellow named Walter Alvarez, who would eventually change the world of science in a quite different way. As for geology itself, its cataclysms had only just begun, and it was young Alvarez who helped to start the process.